Good afternoon and welcome to today's webinar, Challenges and Practical Solutions to Municipal Stormwater Management. My name is George Burgos and I'll be managing the technical aspects of today's webinar. Well, a few housekeeping items. By now, you should have the GoToWebinar application running and see the welcome presentation on your screen. If you're having technical difficulties using GoToWebinar, please go to www.gotowebinar.com and click on the frequently asked questions in the blue navigation bar on the left side of the page. For those of you joining us via phone, there may be some short visual delays. Presenters will pause briefly between slides to compensate. The slides will be advanced by the presenter himself. A copy of the slides is in your handout box. Today's webinar will be recorded. We hope to transcribe it and post it online. When we do this, we will send you an email notifying you. We encourage you to ask questions. Please use the GoToWebinar control panel and type your questions in the area marked questions. Then click send to submit it to the moderator. Feel free to submit questions anytime during the presentation. At the end of the webinar, you will receive an evaluation, which we encourage you to fill out. It also asks for your suggestions on any new webinars that you would like us to consider. Please take a moment to read the disclaimer. EPA doesn't officially endorse or recommend any trade names or commercial products that may be mentioned in this webinar. And before we begin, we would like to do a couple of polls. What job roles are in the audience today? DPW, Stormwater Coordinator, NGO, Contractor, Federal/State, or Other? Give it a few minutes and I'll read the results. Okay, I'm going to close and I'm going to share. So it looks like 25% are from DPW, Stormwater Coordinator, 30% from NGO, 3% Contractor, 29% from Federal/State, and 30% Other. And we're going to do one more before we start our webinar. What is your level of experience operating, managing, and/or funding MS4s? No experience, a little experience, moderate experience, significant experience, or not applicable? A few more seconds. Okay, and I'm going to close and going to share. 34% no experience, 19% a little experience, 22% moderate experience, 15% significant experience, and 10% not applicable. And now with the webinar, today's seminar will be moderated by EPA's Joshua Secunda. We are ready to start the webinar. I'll now turn things over to Joshua.
Thanks, George. I'm Joshua Secunda with EPA's Assistance in Pollution Prevention Program, and today we are presenting Dr. James Houle, Program Director of the University of New Hampshire Stormwater Center. He directs and manages the Stormwater Center's growing body of research projects and is an expert in the design and implementation of innovative stormwater management solutions and control measures. His expertise includes planning and implementation, BMP performance evaluation, O&M costs, and water resource monitoring. He's a nationally respected expert on the implementation of effective and economical stormwater control strategies here in New England and throughout the country. Dr. Houle holds a graduate degree in natural resources and environmental science and is a certified professional in stormwater quality and erosion and sediment control. Today, Dr. Houle will highlight new cost-effective approaches to implementing green infrastructure projects. He has been working with the City of Dover, New Hampshire on research demonstrating that innovative GI solutions can be more efficient and economical to install than conventional approaches and less costly to maintain. Dr. Houle will share results from his work with Dover where such measures are producing superior results, and he'll conclude by discussing the complete community approach a strategy designed to integrate GI into all municipal water resource management efforts. Its findings should be reproducible by many New England small MS4 communities facing the performance and economic challenges posed by stormwater management control. Welcome, Dr. Houle.
Great, thank you very much, Josh. And thanks for having me. It's a pleasure to be here to talk about, amongst many other things, stormwater and stormwater management and practical solutions. So I'm happy to also discuss some of our experiences over the last decade and a half with implementation. So we learn a lot from it. There's lots of great things happening in the stormwater world, and this might be a little bit different from the big stories about the great things happening in the larger cities like Boston and Philadelphia and Washington, D.C. and New York City, amongst others. This is largely a story and some findings from a relatively small watershed that we've been working with in the city of Dover, New Hampshire. So with that, I need to acknowledge and thank our project partners, which is the city of Dover and the majority of their public works staff. Also, New Hampshire Department of Environmental Services that provided much of the funding through 319 funds and other largely passed through from the Environmental Protection Agency, Region 1. So, like many watersheds, the Berry Brook was a small impaired watershed, only about 186 acres, so small and manageable. So like many other watersheds, there was a watershed management plan that we had not had taken part in. And that watershed management plan outlines practical or ways to implement to achieve water quality goals and water quality targets. So we took this on in early 2007, and we started writing grants along with the city of Dover to get funding to implement the watershed management plan. I will say up today that plan is complete, and to my knowledge, it is the first fully implemented watershed management plan in the state. And actively researching what other implementation projects have been, or watershed management plans have been fully implemented. And the reason I bring that up and why that's important is because inevitably, with all the planning, implementation takes on a different flavor. And there's lots of lessons learned and through the implementation project, and that's largely the basis of my discussion today. So if you take a aerial view of the watershed, like I said, it's about 186 acres wide, so in size, so relatively small. It's a multi-use residential and commercial area at about 30% impervious cover, and discharging to the Cocheco River ultimately, which is the main tributary. So the dots that you see on this map are the 26 different BMPs that we implemented throughout the watershed management plan, and our target and our goal was to get an effective impervious cover down to 10%, which we've done. As far as the overall costs, this was not a cheap effort for a relatively small watershed. So it includes about $800,000 worth of grant funds, about $530,000 in community match, and that's the minimum estimate because that's what was required as part of the match requirement for the grant funding. With that, we implemented 26 BMPs. We reduced about 37 acres of directly connected impervious cover, and we have we've also achieved pollutant load reductions. And in stormwater, we particularly target sediment, phosphorus, and nitrogen, although there may be other associated pollutants like bacteria, indicator bacteria, amongst others. Sediment, phosphorus, and nitrogen are the major targets. And in this particular water body, it was impaired for aquatic life use support, and there's no smoking gun, and I guess as close to a smoking gun as we had was the altered urban hydrology from all the impervious cover. So in a nutshell, we did a lot of work. It included a lot of different stormwater control measures or best management practices. I'll probably use the term BMP just for lack of a better term. Not that I like it altogether, but it's probably the most understood and widely used term, best management practice. So we did about 12 bioretention systems, a tree filter, a subsurface gravel wetland. We did wetland restoration, as well as stream daylighting. We did grassline swales, subsurface gravel filters, infiltration trenches, and we had to invent some technologies as well because we started to run out of space. So lots going on. Typical watershed management approach, as you may or may not be familiar with, it starts with a plan. In that plan, largely there's a lot of GIS analysis. You're looking for space to implement BMPs, looking to maximize and optimize implementation efforts, modeling output. So you're trying to get obviously load reductions, or in our case, we were trying to just simply disconnect directly connected impervious cover through appropriately sized stormwater control measures, or BMPs. And then there's outreach and education results, and then the final report. So this is pretty traditional, and this is pretty par for the course. This is kind of, I'd say, the standard for doing business in watershed restoration efforts, particularly with respect to stormwater. Interestingly, we started off with a plan, and as we got boots on the ground, we found that we needed to change some of those planning efforts for whatever reason. Initially, there was a lot of BMPs identified to go into private property. There were some areas that, as we did some more survey and some more investigation, possibly were not modeled correctly. So we did a lot of re-optimization and recalibration of the model. And we finally got funding to implement our first cadre of BMPs. And then inevitably we started to run into problems and issues like this 40,000 square foot subsurface slow sand filter that was built in 1888. Now, aside from just the pure remarkableness of this development, I mean, there's no reinforcement in this concrete. It's exquisitely done, built in the late 1800s, and you know, the big thing for us is this was smack dab in the middle of one of our stream restoration efforts, and interestingly, it didn't show up on any plan. So that we didn't have, despite the fact that this is a rather large utility, it didn't show up on any existing plans, probably because it was built in the 1800s. But still, that being said, it was a kind of a wrench in the spokes of our progress, because not only did we have to deal with this, but it is a historic structure. So under it required a Section 106 permit, which means that's the National Historic Preservation Act, which means we had to go through a lot of documentation, photographic documentation, and it resulted in a few thousands of dollars that we didn't expect to have. And there was a lot of demolition that was involved in repurposing this. So this sat below what was being used as a public works stockpile area, and it was also where we had identified the need to daylight about a large section of stream. This isn't the only obstacle we ran into. In fact, in these small kind of dated watersheds, we ran into lots of obstacles, including private property, including BMPs that folks weren't familiar with or didn't want to use, including utilities that weren't documented, including private property that wasn't surveyed correctly, and we couldn't get deeds or we couldn't get rights of way in order to do ongoing maintenance. We also ran into a lot of, I'll call them differences of opinions with respect to how the BMPs looked and functioned. We naturally came into this with a perspective of what, let's say, a bioretention looked like, and it looks a lot like that picture on the right side of your screen. Vegetated, diverse, native vegetation with, for most parts, at-grade inlets to decrease the amount of structures that we were putting in. And this inevitably led to, a type of design that in our ongoing discussions with the Department of Public Works were not conducive to their operation and maintenance. And so originally it started off, as sort of colorful disagreements. And then we realized quite quickly that, this project wasn't going to go on if we didn't start to listen to the inevitable owners of the infrastructure and maintainers. So that became, a very large part of the learning in this project. So you look at a bioretention like this, as you see on your screen, and it meets all the criteria of a conventional bioretention and what it's supposed to look like and how it's supposed to function. The big difference is down to maintenance. So we had lots of discussions out here about how to maintain this. And, as much as I could have said, you can maintain it easily with, a pair of shears or a weed whacker, and you whack down the vegetation once a year, compost it or haul it out of the system, and that should be about it. It didn't necessarily jive with the local maintenance culture, which was a lot. There's a lot of lawn and a lot of mowing that happens out here anyway. And so, that's one of the things that the DPW could do very effectively. And so, this is what it looked like after maintained. Like I said, I could say, oh, it's relatively easy, but easy is all in the mind of the beholder. And I am not the owner of this system. I walk away from this system, and I don't really have, outside of our monitoring efforts, I don't have long-term ownership. So we really have to be careful, I think, and this is one of the things that I learned, is what we call easy, because like I said, mowing and certain catch basin cleaning is something that the DPW is very versed with and could easily do. So I had to really change my perspective about, what maintenance was, and had to look at kind of the existing maintenance culture of the Department of Public Works, which was the primary owner of these facilities. So compare that to a system up the road, which is what you see here, which is a bioretention system. And I've had arguments with many folks, and it's really, I really hope that we add to the flexibility of this infrastructure, because green infrastructure is inherently very, very flexible, as hopefully I will demonstrate. So this is green infrastructure. It is grassed, and you can take issue with the plant selection, but from a maintenance perspective, this was considered no maintenance from the DPW perspective, because they could easily mow this. So naturally, that led me to think about, well, how does this differentiate amongst pollutant management? And of course, I'm going to leave out things like habitat, and this will not probably create the habitat that a system like this will. But our target was disconnecting large areas of directly connected impervious cover and managing the pollutant load. So that was our focus, because we were dealing with an impaired water. So this is Bill Belanger, award-winning superintendent of public works down in Dover. And as you'll see, when we started to communicate more and we started to co-develop these structures, and the types of BMPs that were going in the ground, we not only increase the effectiveness of it, but we actually reduce the maintenance burden. So Bill's big thing was no plants. And you might call grass a plant, I certainly would, but again, it's from the perspective of maintenance. The grass they could mow, the large flowering plants, required different contracts, which was not easily managed by the public works. So naturally, we asked the question, well, what's the penalty, if there is one, of planted versus grass systems? Again, from the pollutant perspective. And we found no water quality penalty. So what you're looking at here is a chart of the percent removal efficiency of the primary pollutants that we're concerned with in stormwater, which is TSS, is total suspended solids, TP along the horizontal axis is total phosphorus, DIN is dissolved in organic nitrogen, and TN is total nitrogen. The blue bars are the planted bioretention systems, an average of 3 that we had studied elsewhere, and the green bars are the grass bioretention systems, again, areas that we had studied. The vertical axis is just the percent removal, so the higher the better. And what you see here is no clear trend or no clear penalty. There's nothing, at least from my perspective, that would make me require that the city planted their bioretention systems as to grass them. And again, I think I take a big picture outlook on this, and what we hopefully are doing is not necessarily is expanding the toolbox. And I'm not saying one's better than the other. I'm not saying that planted systems do not have their benefits, such as habitat and other things, but I'm really looking at the primary objective here was to reduce pollutants, and the owner of the system was clearly saying that they preferred a certain maintenance regime that we could easily give them with a different type of design, or not a different type of design, a different type of planting array. So we grass systems, and now they mow them. And as you'll see later, I am a maintained BMP is a great BMP in my book. We've spent a lot of time looking at optimizing BMP performance for different pollutants, but in the end, if you're not maintaining it, then I question what the optimization that we've done in our analysis is worth. We can look at other things like infiltration rate, and planted bioretention systems tend to start off with high infiltration rate, surface infiltration rate. So this is in inches an hour, but we see that rate diminish over time, largely because the plants themselves create preferential flow paths through the system and kind of concentrate the sediment. So you get a reducing surface infiltration rate over time, whereas a grass system is evenly vegetated throughout the entire system. It's relatively flat, so you get even distribution of water, meaning that you're covering the whole entire filter, and the roots themselves, while not excessively deep, create and enhance a macropore. So it maintains infiltration capacity. So here we see an increasing trend over time, where the planted systems started high and reduce over time. The grass systems, outside of mowing, I don't think these are going to need to be raked out, whereas the planted systems will need to be raked out over time in between the plants. And I want to also illustrate this because we see a lot of great planting regimes. And again, I don't want to come across as anti-plant. I just want to demonstrate some of the utility of these designs in the long term. So this is a design, I believe I eliminated much of the implicating factors here to protect the innocent, but this is what we typically would see for many designs for a bioretention system. And all these different colors are associated with a vast array of plants. So great work from a landscape architect side. Someone really thought about the planting regime, what plants would do well in what zones of the system. But I would caution that they potentially, the oversight here is the long-term operation and maintenance. And so this is a system that went in the ground, it was planted. I don't know what this planting regime costs, but it's very complex and well studied, obviously. But the result here, and I'll show you what this looks like now. This is taken yesterday. And we have, aside from this diverse array of plants that were initially installed in the system, we now are overoccupied with typha or cattails. So over time, and this is likely due to some lack of maintenance, right? Because these plants don't just take care of themselves. I mean, the gardening industry is $1 billion industry in the country. And that's because people enjoy taking care of plants and facilitating their growth, but it's not without maintenance. You have to weed, you have to keep out invasives. And, you know, here the conditions were such that it really, I guess, that the typha just flourished. And without long-term maintenance and without routine weeding, this is what happens. So I just say that as a note of caution, because we've spent a lot of time, I think, in stormwater, putting the cart before the horse, prioritizing certain things before others. And hopefully our experience and some of this data, which is all fundamentally based on data. I don't say, you know, just from opinion that grass systems, there's no water quality penalty compared to vegetated systems. And I admittedly am not looking at the whole range of benefits. You know, obviously looking at just the water quality benefits, because we're dealing with largely urbanized areas. But we've collected the data that underpin many of these comments. And you know, as any emergent field, there's not a lot of data. It's a growing field, and there's growing bodies of data, but there's a lot of opinions out there about what works best. And I'm not refuting any of those opinions. I'm just saying that long-term operation and maintenance is really a really important discussion. And we can't put the cart before the horse because we can't assume that operation and maintenance is happening. And when it doesn't happen, we know the results. The systems don't function. So being upfront and honest and taking it on head on in the beginning and the planning stages is a good way of heading off some of the mistakes that we've made. And I do this routinely. Just Google bioretention design, and the last time I did it, maybe 3 months ago, I got 381,000 results. 381,000 results for how to design a bioretention system. That's a lot of information. So we're not, you know, we're dealing with a lot of information. I don't know how many of these designs have been tested and monitored and maintained and reviewed and assessed, but I would say it's a small fraction. I'll leave it at that. A small fraction of these. So we're dealing with a vast amount of information. We're dealing with lots of ideas about what these systems are, and we're dealing with a fraction of the type of data that we need to fully substantiate not only system design, but long-term system operation and function. And I say that because we do a lot of this on the watershed management side, and we do it from an engineering perspective. The result with Berry Brook in this 186-acre watershed is not one of the systems that we designed on a computer in CAD was installed as originally planned. And that's largely because we were dealing with small sites, and we were dealing with areas that, for the most part, we hardly could size the system at all. What we could do is fit what we could fit. And then we needed to develop ways to calculate the benefits. So this really changes the design. And when we did think we had it nailed, and we did some investigation, inevitably, when we started to dig, we found something that we hadn't expected: a utility, an old property that we couldn't fully survey. The list goes on and on. So if we keep the overall goal of disconnecting directly connected impervious cover, then flexibility really ruled the day, and we had to be flexible. And we found that overall this was largely a benefit, because as we worked more with the DPW and we got a sense of, one, what they could maintain and what they wanted to see, Bill, the superintendent, took over and started inventing new systems, which really is what keeps me going and what gets me excited is someone on the ground with a practical understanding of how these systems work say, oh, that's what you want to do? You want to put water back into the ground? Well, I can do that a lot easier than you can. And he's actually invented, he's on his 4th BMP that he's sort of inventing or reinventing. And I think that to me is a LID, or it's a green infrastructure renaissance that's only waiting to happen. And we have to be flexible enough to allow these things to happen and increase the size of our toolbox and not get into discussions about, what is or does not constitute a fire retention system. So, like I said, some of these systems originally, we had optimized the placement of porous asphalt all over the watershed. We know porous asphalt works. We know it enhances infiltration, particularly through good soils, which we were dealing with a lot of A and B soils here, and we knew it could work. We also had colorful discussions about porous asphalt, and Bill he didn't want it because he didn't have a vacuum truck. So porous asphalt has distinct maintenance requirements. It requires vacuuming and inspection, and the city did not own a vacuum truck. They owned a Vector truck, but not a vacuum sweeper. So he preferred deep sump catch basins on the front end of these systems, and systems that they could, and that would be the primary maintenance point. So, we pushed it again because we had done a lot of optimization, and we knew that strategic placement of porous asphalt could do a lot. And finally, I think Bill said, over my dead body, which that's when I finally kind of gave up. I think that didn't leave a lot of room for negotiation. So we went back to the drawing board, and we really found, or my big learning was that green infrastructure is inherently flexible. So we think of porous pavement, I like to think of it as a system where the porous pavement itself is just a hydraulic inlet. That's how water gets into the system. But everything else in the subbase is designed for storage and filtration of water. So we played a little bit with the design, and we designed a porous asphalt subbase cross-section where we had sand on the bottom for filtration, and we had stone on top for storage and voids. And then we actually went with a regular pavement on top, and deep sump catch basins as the hydraulic inlets that were interconnected with slotted pipe. And that was the hydraulic inlet. So it's kind of a sneaky, it's a porous pavement without the porous asphalt. And it met the working criteria for us, and it met the maintenance criteria for the DPW. And this has been, we've monitored this, and it's working really good. Here's some of the data. What you see here is along the vertical axis, you just have real elevation. That's the elevation above sea level. And you see a little cartoon of the system. So we have the outlet on the bottom, and that would largely be controlled with an orifice control to get our storage. So the design criteria is you store the water quality volume, which is a 1-inch rainfall event, in the void space of the stones. You let that through an inlet, which is high. You can see that inlet is right around 98.6 elevation, the invert. The outlet is low, and that outlet has a restricted, like an orifice restrictor to let the water out slowly to get our storage time, reduce peak flows, and enhance infiltration through the sand and into the soil, native soils. And you can see the results here. So on the horizontal axis, we have time. So this is just a 6-month monitoring period. You see rainfall on the right-hand vertical axis, just as a depth in inches, and then you can see those lines dropping down. So we saw some pretty big rainfall events. The biggest one was 1.43 inches, and on the bottom you see this dark blue line, and that is water level within the system. So the dotted gray line right under the system full, that was the design. So a 1-inch rainfall event from the drainage area should fill the system up. And as you can see, throughout our monitoring period, we had large events greater than the design, and we never filled the system up more than halfway. And what this tells us is these systems are far more efficient hydraulically than we model them, because we know we get exfiltration out of these systems in all 3 dimensions, not just vertically as we model the design, but also horizontally through the sidewalls. And we've seen this in other instances. And as I go further in the presentation, this leads us to more flexible sizing. So in Region 1, thankfully, in new development, we're committed to the water quality volume sizing, which is the 1-inch rainfall event. But in retrofit, where you have a lot more limitations, we actually have a flexible crediting system that EPA Region 1 has developed performance curves, which I'll show you a little bit later, that allow us to take credit for management for less than the water quality volume. And you can see here why, because these systems we design these systems very inefficiently. We generate a volume from a rainfall event, like a 1-inch rainfall event, and we kerplunk it in the system instantaneously. But that's not really how it happens in the real world. We know when it starts raining, we go from long duration storm events to short duration, high intensity, and it fluctuates as water is delivered to the system. And these systems hydraulically are far more efficient than we model them to be conventionally. So we start running out of space, and we have to deal more and more in the right of way. And so this is the second innovation that Bill had come up with, where they were doing drainage improvement in this area with good soils, nice sandy soils. And so he came up with a perforated line, basically in between 2 catch basins. So slotted pipe instead of solid pipe. And then the trench would be over excavated, backfilled with stone. And then we put geotextile on the vertical walls and leave the bottom open, largely so you maintain both the horizontal and the vertical flow path. So this is a pretty simple modification to a conventional design. I think the marginal increase in cost here is about 10%, largely to do with the added stone, because there's no real cost increase going from solid pipe to slotted pipe. So we get enhanced capacity, and if everything would fail, let's say in the long run, it would still operate much like a solid pipe would. But we have some catch basins on either side in order to knock out the large sediment areas. And with these BMP performance curves now with Region 1, we can actually credit the system. The sizing, it's actually sized for a 0.1-inch rain event. And traditionally that would almost seem laughable. But we've seen and we verified through field empirical data that these estimates are pretty right on, largely because they do a better job at modeling that dynamic hydrology. So you get a lot more reduction of volume, especially in areas where you have better soils, because that rainfall distribution is dynamic. It's not static or instantaneous like we model it. So we can see it about 700 cubic feet of stone. That was the differential cost. Then if we had just bedded this in, your standard 6 inches of stone, and now with the performance curves, we can estimate the treatment performance, and we can actually take credit for that disconnection of impervious cover. Finally, the last innovation, or actually I'm going to cut it short. He's working on the 4th now, and I don't have detail on that, but it's kind of one of the things that's great. They're always coming up with something new. And then we come in and we test them, or we help them design the system so that, it's meeting our criteria as well. And that's been very, very successful. So because we started to run out of space, and we started to run out of space to work in, and we didn't want to deal with private property because, again, maintenance is paramount, and we need maintenance access, and the city has to maintain these systems. So we are kind of forced more into the right of way. And so we, working with Bill, we came up with, I would call it an enhancement on the deep sump catch basin. So the deep sump catch basin has been around for almost half a century. And, you know, it's been about as good as we can get for water quality or pretreatment. And so what we did is we created a sectional media box filter where we could include the functionality of a deep sump catch basin, the maintainability of the deep sump, but I'll also take advantage of enhanced treatment through a filtration area. And these are designed to go underneath the right of way, and they're designed in sections. So you can add sections, just 4x5 sections as your drainage area increases. So every one section will manage about 0.25 acres of impervious cover. So if we have more drainage area to treat, we add more sections, and you can buy that. We work with a precast, and these, we've got the cost down now to about $2,400. And if I'd played my cards right, I would have gotten, I would have handed out a lot of disclosure agreements, non-disclosure agreements. We would have gotten a patent on this, and we could have added a 0 or 2 to the cost. But, you know, obviously, we weren't that savvy, and these are now being sold in the area for about $2,400 each. So, you know, a increase over a standard deep sump catch basin, but we're now monitoring this to dial in the pollutant performance. This is what it looks like going into the ground. This is actually the 3rd generation. The 1st generation, we didn't have a lot of consultation with the DPW, and we came up with something that couldn't be moved with a backhoe. And so that became kind of one of the guiding design features, because, you know, they weren't going to pull in large, heavy machinery to move a big hunk of concrete around. And that also added to the sectional feature. These sectional features are just 4-foot by 5-foot sections that can be installed with a backhoe. This is the front end section. On the front end, you see the it's just a rectangular deep sump. There's a grate to help with floatables and organic debris like leaves, and then you can see the first section of the filter media going in. There's a couple more. It's going in with a backhoe. That's the fully complete system. And then we have standard details for this now. Something else we're trying to develop, standard details, so we can just provide them to other public works departments that want to begin to experiment with this. We have conventional media, which is basically sand, and we use a water treatment residual to enhance phosphorus absorption. That's our special sauce, but there's lots of other things that we can experiment with. We're working with a company now to start to test other media like zeolite and other expanded shale style media that can enhance other pollutant removal. And we can test it. So we can swap in media, swap out media, and the structure itself is just concrete. It has high flow bypass contingencies as well, and it has holes around the perimeter to enhance exfiltration and volume reduction through infiltration. And small storm events it'll treat, large storm events it'll bypass, just as a deep sump catch basin would to the storm drain. So we started to monitor these things. I've just instrumented it this spring, so we've been I haven't downloaded the data yet. I wish I could have done that for this, but we're optimistic. I've done visual inspection, so here's the deep sump on the front end, and we can see about we've collected already a good 8 to 10 inches of sediment here just from a winter, and that of course can be vacuumed out with a conventional vector truck. And then this is a close-up of, we have a 30-inch diameter maintenance hatch. I pulled the maintenance hatch. This is a close-up of the filter media. So you can see that a film starting on the surface, And if we just scratch that a millimeter below the surface, it's just a thin veneer of fines. Just below that, we get into that nice sandy soil. So I've just scratched my finger, and you can see we're tapping into that nice sandy soil. So the sedimentation and a lot of the filtration really happens at the surface. And now we're designing tools to maintain this. So this is a picture on the right of a new tool that I just got in today. This is a picture of it. It's really a asphalt lube. And what we're doing is we hope to be able to just scrape the surface and vector it out when we vector out the deep sump catch basin. So we'll be working with the DPW to make sure that this is not overburdensome. So this all really speaks to a new project approach. If we remember the old project approach, where we did a lot of analysis, a lot of optimization, with very little experience with our toolbox of BMPs. We're kind of flipping that around, and we're saying, hey, we can do simple analysis, desktop analysis, right? We don't have to spend a lot of time and a lot of effort and a lot of expense modeling a watershed. Let's do simple analysis, identify sites, and try to get out in the field as soon as possible. Because when you start to implement and you start to put BMPs in the ground and boots on the ground, inevitably your approach may change. And I say may, it's always changed for us. There's been a lot of learning on the front end, and I would be more confident in our design ability if we weren't still doing demonstration projects. Well, you know, this is a decade and a half we've been doing these, and we're still doing demonstration projects. So in the Berry Brook, this is the closest we've come to implementation, like full-scale implementation, where now the city has these new generation of filter and catch basins that they're implementing, not just in Berry Brook, but in other areas that are suitable. And again, developing new approaches for suitable areas. And so we feel like we're increasing the toolbox here, and these are all practical innovations, not dreamt up at our research facility, tested by our research facility, but I guess developed through this partnership that we have with the people that actually are on the ground with the responsibility and authority to act. So they're really helping us adapt our textbook research-based designs. We can have it both ways. That's been our experience. We know what works, and we can sprinkle that in on the side, and the DPWs know what works and know what they can maintain, and I don't see a reason why we can't work to co-produce new innovations that are better and cheaper and more effective. So that's the dream. I'm sticking to it. We've had great experience in Dover, and when I look at the sheer opportunity, I'll say opportunity, not task, but the opportunity that exists. Dover is the largest city in the seacoast and in the coastal watershed here in New Hampshire. It's about 30,000 people, and they have over 2,800 catch basins, 65 linear miles of stormwater pipe, 200 outfall locations. That's a lot of infrastructure. It's on par with the wastewater infrastructure, minus the energy inputs and minus the end of pipe treatment. But we don't do end of pipe treatment of stormwater. For the most part, the conventional approach was get it away, drain it to the receiving water as quick as possible. So we have a lot of work to do to begin to intervene and begin to opportunistically improve that approach. But we feel like there's a lot of opportunity out there, and this kind of introduces, I guess, we know it's not going to happen overnight. This introduces a new approach where it might be a parallel approach to the big optimization and watershed management plans, because we know we're updating this infrastructure opportunistically over time. And if we can improve it here and there, and we can take advantage of suitable conditions, I feel like we can make major progress. So here's the other cart before the horse. This is another great story from the field that almost single-handedly, in addition to the Berry Brook plan, this really changed the way we approach designs. This is a project in another coastal city here in New Hampshire, a great award-winning project. It was part of a combined sewer overflow separation where they used innovative things like tree box filters, subsurface sand filters to disconnect not only a sewer, but create a secondary stormwater sewer and create inline treatment along that conveyance. So lots of stuff went in the ground. We monitored it the first year. Here's, again, a removal efficiency plot. Here we're looking at, you see total suspended solids down there on the horizontal axis. We've introduced a new total petroleum hydrocarbons, TPHD, zinc, total nitrogen, total phosphorus, and removal efficiency on the vertical axis. So really good performance, mimics what we found in the field, on our site, on our research facility, as we looked at these systems, and we know it's very comparative. So this is the same plot, and it compares the tree box filter in the field with what we've tested at our research facility. And it's almost lines up line for line, with the exception of total phosphorus, and I won't get too much into that, but that has to do with absorptive capacity and non-maintenance. This is a location here where you see in the picture, that's a subsurface sand filter. So great design, award-winning design for street separation. And, you know, we monitored it for the first year, and the city asked us to come back and monitor it after 7 years of operation. So we monitored the outfall of the stormwater conveyance, and we monitored a adjacent drainage area that simply had catch basin structures and pipe. So, you know, it's our control. So we had the green street, if you will, the green infrastructure street disconnection side by side with a conventional catch basin pipe. And this is the sobering part, because we came back 7 years later and we saw no maintenance. And this is not casting a blame. If anything, the blame falls on the engineering side that didn't adequately discuss long-term operation and maintenance with the owners. So we lift the hatch on the sand filter and we see the subsurface sand filter, and we just see dirty water, never been maintained. This is a picture from the gloomy innards after we drained it, and you can just see it's just mucked up. I said mucked. M. That's the technical term here, I think, for this. So we tried to maintain this, and we really had no good tools to maintain this. I mean, this is a confined space. We couldn't really send a lot of folks in there without, you know, lots of permitting. And so we're working with the DPW now to come up after the fact, right? This is 8 years too late to come up with maintenance tools to maintain this. And we haven't gotten that. But that would have been a perfect conversation to have before the system was even designed. And so that is really on the engineering side. I would like to say that this is a unique problem, but I see it over and over again. Very seldom are the system owners even included in design discussions. And I think particularly for municipal operations, that needs to change. Because, oh, where's the data? Oh my goodness, I apologize. I didn't add the data. So when we went back and monitored this, it might be in your presentation in the handout because I was playing with this, unfortunately. My curse continued to manipulate these things. But when we looked at the data, and we looked at the sediment and the phosphorus and the nitrogen, and we looked at the green infrastructure system after 8 years of operation and no maintenance, and we looked at the adjacent control of just conventional catch basin pipe, we saw no statistical difference. The bars kind of just line up. And that is very sobering for a researcher. I know these systems work, but we didn't understand the effect and the impact of the long-term operation and maintenance. So now it really puts it really changes the way we approach system installation, because I would almost venture to say at this point, and I might be going on a limb here, that I'd rather put in an inferior BMP, so a system that might not filter or treat stormwater pollutants like we know that other systems can, if I know it's good and I have assurances that it's going to be maintained. I think I'm more comfortable with that than going with a system that might win an award in the first year, but maybe the tools have yet to be invented to maintain that system, and it's just going to get neglected, because over the years that system performance is going to approach and eventually get to zero. So take that from the school of hard knocks. And I know these are some of my favorite pictures. I know that maintenance is not a foreign concept to us. We maintain, we often joke, right? I want a no maintenance system, but that's a little bit, that's a really bit of a false choice and a false narrative, because we don't necessarily want a no maintenance system. We want a system with maintenance that we understand, and maintenance that we have tools for, and maintenance that we can implement. And this is a great picture, right? This is a road. This is actually in northern Michigan, where my wife is from. And on a bike trip, I came across this road, and in my mind, I'm thinking, wow, these are folks that understand how to seal coat or cracks, and that's a lot of time and energy. And I know, and I'm looking at this further down the road. It gets, oh, sorry, some of my slides are messed up. So further down the road, there's more, right? And this is a little bit like art. So, and I know that because down another corner, they had signed their name, right? So these are people that take pride, that know how to do this. So I guess my point is, we need to understand how maintenance occurs, what the culture of maintenance is, and I have a strong feeling that green infrastructure is flexible enough that we can design it to meet whatever that is, that culture of maintenance. So I'll back up. I apologize for mixing up the slides. There's the data. I wasn't lying to you. The green is the green street. The blue is the conventional straight up catch basin and pipe street. And here we're looking at sediment, nitrogen, and phosphorus along the horizontal axis, and the vertical axis is concentration in milligrams per liter. And note the log plot. So this covers 3 orders of magnitude. So sediment is in higher concentration than nutrients, but the trend here is quite clear. There's no clear distinction statistically of performance of the green street to the conventional street. And I have to hang this all on operation and maintenance. And I think I'll end there, because I do have other slides. If there's more time, I thought this went to 2, but I'd want to take at least a short break and address questions. And if we do have more time, I can show you the data from Berry Brook. And
Jamie, we have till 2:30.
Okay, all right. So I'll keep going. You want me to keep going then?
Yes, please.
Okay. So these are the performance curves I wanted to talk about. And this is, if you're from Massachusetts or from New Hampshire, you are well versed that we are now the recipients of a new MS4 permit, and we're non-delegated states. So EPA Region 1 has developed our permit for us, and that gives some people heartburn. For me, there's a silver lining to this, and we have these performance curves, and this is pretty groundbreaking. And this, I think, will reduce the cost and increase the flexibility of implementing green infrastructure particularly for retrofit scenarios. So when we talk about regulations and controls for new development, we don't think that any of that is going to change. You know, with a new development, you have, it's your blank canvas. So you can do what you need to do. The bar is relatively, it needs to be relatively high because you have a lot of flexibility. On all of the existing landscape that we have, our existing urban centers, flexibility is the name of the game. And these performance curves really give that to us. So in any other part of the country outside of the Chesapeake Bay program, if you don't treat the water quality volume, that 1-inch rain event, then you get no credit. So it's kind of like, you know, I tell my students, it's kind of like, you know, getting 9 out of 10 of the answers right and getting a 0. And so that just didn't seem right to many of the I guess, innovative thinkers at Region 1. And so they put a lot of work in developing these performance curves such that we can take and we can credit system and we can get load reduction, sediment, phosphorus, nitrogen, and even volume reduction, which I don't show here, but those performance curves can model volume reduction, and we can do it for less than the water quality volume. So the permit is very explicit on how to calculate this. We've also incorporated this in a new program that we have on our website called PTAP, and we have explicit instructions on how to calculate the design storage volume. So you can get it from Appendix F of the New Hampshire permit or the Mass permit. New Hampshire permit's good because we also added nitrogen in there, or you can get it from our website, unh.edu/UNHSC, which I think I have documented later. And what's fascinating is we've actually studied these systems in the field. And I'm not going to go into it in this presentation, but I have a whole presentation on an undersized system. We have a paper that's out that you can access from our website on this very study. And it's basically empirical validation of these performance curves. And so here you're seeing largely the empirical results. We have the tabular performance curves that are available in Appendix F of the permit. And here you just figure out the design storage volume, and that equates to a certain depth of runoff treated. You find that on the horizontal axis. You go up vertically to where it intersects your pollutant of concern, or if you're looking at volume reduction, and then you go over to the vertical axis and you get your pollutant load reduction. So we actually tested a system, 2 systems, one a biofiltration system and one a subsurface gravel wetland that were sized that had a design storage volume for a 0.1-inch rain event and a 0.23-inch rain event, and we studied it for a period of 2 years. Here's the results in the tabular data below the curves, and we have depth treated, modeled removal efficiency from the curves, 48% TSS removal, 57% zinc removal, 55% nitrogen, 19% phosphorus, and then our measured removal efficiencies. And you can see from the measured, we're pretty much on target or exceeding the model reductions on every case, with the exception of total nitrogen. And we feel like that is more of an engineering side, and I don't have time to talk about all that, but we feel like we can get there pretty easily with some changes in our conventional approach to design. So this is great news. We've essentially, through this paper, validated the effectiveness of these performance curves, and we've already demonstrated that they can actually save costs. And I don't have this in here, but we work with Boston Water and Sewer. And John Sullivan, also another local champion here. He's the head of Boston Water and Sewer, and we work with him to design a system to meet the 62% phosphorus reduction in the Charles River watershed as part of a TMDL, and save over $2 million using these performance curves. So we know it works, and we know it increases flexibility, and it's going to save us money over time. Also, a great resource that not many people know about is these Region 1 cost estimates. So we exclusively use these cost estimates when we're doing our estimation for what these types of systems are going to do. And the great thing is it's all a common denominator. You reduce everything to design storage volume and you get a cost. And then there's simple cost multipliers based on the complexity that you anticipate. Like if it's an ultra urban area and you think you need a police detail, there's a certain cost multiplier that you can add to that. This is available on our website, or there's a long URL that it's also available on the Region 1 website as well. And this is great information for doing cost estimates. And interestingly, you know, here's a plug for ounce of prevention is worth a pound of cure, because we don't have a TMDL yet for the Great Bay. And nor do I want one. I would rather do these cost-effective implementation plans. I would rather have that flexibility, and I would rather do things more opportunistically, because we know if we ignore the problem, the costs are only going to compound. And that can be, I guess, illustrated by, you know, the typical cost per disconnection of, or a greened acre, if you will, if they call it in Philadelphia, or disconnection of an acre of impervious cover, which a lot of these larger communities are investing a lot of money and a lot of good science into fixing combined sewer problems. But, you know, the cost for disconnecting impervious cover in New Hampshire is about $30,000. And, you know, as you increase the complexity, obviously, and the need for, and the urban, you know, the costs go up. So I'm advocating here that, you know, we tried to tackle this problem before these numbers start to creep up. So, and that all largely comes down to local champions. And we really like, where we do have local champions, we like to highlight the innovations and what they're really promoting in their area. So Bill Belanger on top, receiving the 2016 EPA Environmental Merit Award, and since also receiving other awards, John Sullivan on the left and Clay Mitchell on the right. He's the planner for the town of Newfields, also done a lot on addressing stormwater regulations, which are a whole other presentation. And it largely comes down to an approach. And I'm very interested in diffusion of innovation, which is a whole science in and of itself, about how innovations not only diffuse, but actually get improved through implementation over time. And, you know, there's a detailed process by how that happens. But I wanted to identify that with particularly stormwater infrastructure, there's a lot that's riding on implementation. Because if we don't get to implementation, we don't have these, we don't learn what we can maintain, we don't learn what works, and we don't learn a lot about the BMPs in our toolbox, and we certainly don't expand the BMPs at our disposal. So implementation is really important, and I hope that underscores kind of some of the lessons learned throughout the Berry Brook project, because if we hadn't gotten to implementation and we hadn't started to try to do this, we wouldn't have come up with all the innovations, and we wouldn't have you know, come up with some of the learning that we had throughout this process. So implementation is necessary to improve and adapt and innovate your toolbox of BMPs and further optimize placement, right? Because if we hadn't gone to implementation, we could have just continued to do watershed management plans where we were optimizing porous asphalt placement all over Dover, and we would have never come across the fact that, you know, Dover really doesn't have the infrastructure to maintain it. So that's just that story kind of repeats itself. And I guess one of the last things I have is, this is the Gartner hype cycle, and it's poignant to me and applicable because it's actually was developed to explain how new technologies permeate the market, and particularly IT technologies, so information technologies. And what you see is a lot of, when new technologies come out, there's bold promises and there's a lot of initial excitement and enthusiasm about it, but there's not a lot of information or details about when these technologies are going to have a return on their investment, or when these technologies are going to pay off in the long run. So the Gartner Hype Cycle really gives us a graphic representation of the maturity and adoption process with respect to technology. And I put stormwater technology right in here. And I would say that, early on in the GI and the LID, low impact development movement, there was a lot of expectations, and I would say in some respects inflated expectations, right? Because we know porous asphalt can work. We don't have a lot of information on the maintenance side, other than it needs to be maintained differently. So, you could say that we're maybe falling down into the trough of delusionment, where I've spent a lot of time in the trough of delusionment. And, that's where you get a lot of decisions to reject, right? If you don't have a mature and long-term relationship with your ultimate BMP owners, and you don't have an ongoing two-directional, two-way communication with them, essentially they're going to be like, these guys are trying to put porous asphalt all over the place. They don't understand our concerns, and I think they're full of crap. So that's where I've been, and I think our experience with Dover and some of these other areas like Boston Water and Sewer, where we're actually co-developing these technologies, I think now we're climbing that slope of enlightenment, and we're going to get to a place where we have better systems that can be easily maintained, and we can co-create and co-invent the tools that are going to maintain these systems. And I think it's going to look very different. So it's very exciting. It's a very exciting time for me, because I think if you've been stuck in the trough of delusionment, at least I think there's hope. We're on the uphill battle, and there's a lot of success. And I would say we've benefited a lot from participation with these folks because they add credibility. And academics have credibility, but only in certain circles. And we don't often have lots of credibility in in public works circles, because the reason being because we focus a lot on optimization, we focus a lot on the science, and we don't focus a lot on the practical side. And so if we can create these working relationships, I think, like I said, it's kind of like chocolate and peanut butter to me. We can kind of have it both and get something better than each on their own. So I'm going to, yes.
Yeah, I wanted to make sure we had some time for questions.
Yes, thank you for stopping me. That's my stopping point. That's the URL for the final report that's available for the Berry Brook project. If you really want to dig into the data, it's all there. And thank you for your attention.
Okay, here are some questions from the listeners and viewers. A couple of compliments first, thanking you for paying attention to the workers on the ground and their participation in doing this, because that's where real change begins. And another listener says, this has been really helpful because our city will not maintain planted GI systems. They will only do it if an NGO or somebody else will do the maintenance. So they're interested in your comments about specific grasses or other mobile plants. Are some better than others to plant in these BMPs? And are there pro and cons from an impact or maintenance perspective?
Yeah, it's a good question and something we hear often. And again, I'm not a plant expert. I designed stormwater BMPs. We study the performance, and we're largely studying the pollutants associated with stormwater runoff. So there's a range of plants that you can select. New England wetland plants is a great resource. I use them. Oftentimes they have different seed mixes. So, I mean, you can have grass systems that, like our meadow flowers, that can be mowed. You know, you can have different grasses. I can't comment on are some effective than others. I can comment that the maintained ones are more effective always. And so that's the only thing I can really comment on. You know, I think it boils down to what is the maintenance expectations of the owners. And some owners want, you know, you got beautiful pictures of rain gardens in front of you. You know, this is habitat for pollinator species. This is all kinds of ancillary benefits, including beautification of the site. But we have to be clear about the objectives. Is this a beautification project, and is there an owner that's interested in it, or is this a stormwater management project? Because they're not the same. And I guess I'll leave it there.
Okay. So another asks, how narrow and deep can you make a grassy swale and still have it be mowable?
Yeah, so that is a good question. We like 4-to-1 slopes for maintainability. Oftentimes, you know, that's easier said than done, especially in these tight situations. 3-to-1 slope is the absolute max, unless you're going to hand mow it. So anything greater than 3-to-1 slopes probably are not going to be amenable to heavy equipment, and will have to be hand mowed.
Okay, have you gathered any data on how often the media and a media filter box is effective? Is there a general schedule for media replacement, or do you do regular monitoring to determine the removal efficiencies over time?
Yeah, that's a great question. So we've only just begun monitoring the media box filter. You know, every answer to this question has a lot of caveats. For the most part, a lot depends on the water that you're treating and how dirty is it. That said, you know, because how dirty the influent water is, it really determines your maintenance burden and your maintenance cycling. High urban areas tend to be dirtier. High urban areas also tend to be full of urban debris like cigarette butts. So we've created, you know, inlet screens just to filter out cigarette butts, so we can maintain those and they don't clog our outlet. So there's no hard and fast right answer, but I will say that the vast majority of the pollutants accumulate on the surface. So we don't really look at, when we look at exhaustion of media, it's largely with respect to some pollutant like that will be sorbed, like phosphorus. So phosphorus is removed from sorptive capacity, and if you fill the sorptive capacity of the soil, you need to regenerate it, and that could be just as easy as putting some media amendment on the surface or resurfacing it every 2 to 5 years. You know, that all depends. But for everything else, for sediment and sediment-associated pollutants like hydrocarbons and metals, it's really all collected in the schmuck on the surface, and you can scrape that off and you can remove it. It's really only in the first couple millimeters or first inch or so. And even if you don't maintain it and it completely clogs, you can scrape down through all the surface sediments and you can restore the infiltration capacity, because you're tapping right back into the original soil. So I don't think there's an exhaustive component for sediment and sediment-associated pollutants. Phosphorus, if that's your concern, yeah, we're gonna have to talk, but it's relatively easy.
Here's a question from Kenilworth, Illinois. They're experiencing durability problems with porous asphalt, and they're wondering if you could describe some of your success using it.
Yes, durability problem. Well, oh wow. So this is we gotta parse this out a little bit. There's durability problems if you're talking about spalling and raveling of the surface. You have to look to the newer specifications of the asphalt binder. If you go to our website, we have a specification that was just updated in 2016. We almost exclusively require polymer modified asphalt binder, and we've had great success with that from a durability perspective. So I would encourage you on that respect to look at our spec online. Beyond that, you have durability with respect to lack of maintenance. And we just found that, you know, these things need to be swept, vacuum sweeper preferably, and, you know, twice a year. Also could be coupled with potentially like litter removal. Like if you have pavements, permeable pavements in areas where there's a lot of leaf debris and leaf litter, you know, you might want to couple that with leaf blowing or removal of that in order to prevent the sediments being ground down. Also limiting run on. So areas where concentrated runoff comes onto your site. That's obviously going to increase the maintenance burden. So that's a couple of quick hits on some of the durability factors. It's not your porous asphalt. There's been a lot of innovations with respect to the design and the asphalt binder content.
So here's a question from Miami, Florida. They're dealing with coastal communities between 8 foot above and it looks like 1 foot below sea level. And they're wondering about the potential for the systems you've been talking about to not only clean stormwater, but to sequester it as well, because their sea levels are rising there quite rapidly. So they're wondering about the potential for subsurface gravel wetlands to provide a place for water to go. And if you think there are better approaches to sequestering stormwater.
Yeah, it's a tough spot. You know, obviously systems need to be designed with respect to the site-specific conditions. I do think a subsurface gravel filter, and again, these aren't wetlands, only because, you know, we're largely storing and filtering water in the subsurface of transportation infrastructure. So parking lots, roadways, you know, historically, water was not supposed to be in the subbase of road infrastructure. And that's the conventional approach. You know, water is the enemy of most transportation infrastructure. And I see that changing. So I do think that the subsurface gravel filters and transportation infrastructure are great areas to have these co-benefits. So it gives water a place to go and allows it where possible back into filter through the native soils.
Okay. Another person is wondering where the data came from for your pollutant removal efficiency study. Were you testing your own BMPs or were you using published research? And if so, can you provide access to the reference data?
Yes. So for the most part, all the data that I showed has been generated by us. So it's there is published data available largely through the International BMP database, which is another good resource. But everything that I showed you is largely our data. A lot of it is online on our website. And if you feel free, hopefully you have my contact information and feel free to email me if something is not readily accessible to you. I know, you know, that's the quick answer. Go to our website and then it's like, well, where? So feel free to send me an email and I can send you a link to the publication.
Okay.
Oh, and I'll add that we have a lot of our data also published in biennial reports that we've done about 5 of them now, and there's a lot of information in those reports as well, and that's on our website under pub specs and info.
And here's another. How high do you mow the grass in Dover? Hopefully at least 3 inches. And when you do it, do you remove the clippings?
Yeah, I don't micromanage that. I'm not exactly sure what their approach is. from the stormwater management perspective, you know, the taller the grass, the better. But yes, we do ask them to remove the clippings because that can be, you know, those can re-release bound nutrients over time.
Okay, and I'll add one more. What's the ponding depth for the turf bioretention, and how fast does it draw down generally?
So for the turf bioretention that you saw, the ponding depth was 6 inches. Traditionally, the ponding depth for most of our bioretention systems doesn't exceed that. That's the convention. I don't see why it couldn't exceed that, but you know, you get into competing factors of, you know, basically can the vegetation sustain that type of ponding. So oftentimes it's 6 inches, probably 12 inches max. And the other question was, there were two parts to that.
That was the clippings question.
No, the draining, the pond.
Oh, how fast did it draw down?
So, you know, the design, the design is a 24-hour drawdown. So that's how we design it. And we have high flow bypass contingencies to make sure we can maintain that. We have under drains that make sure we can maintain the 24-hour drain down, and that's all largely for vector control. However, I'd say the way those systems operate is they're far faster. You know, typical drain down for those systems is probably within 4 hours of the end of excess precipitation runoff. There's no more water.
All right, well, I think that about wraps us up. I do want to respond to multiple questions by saying that this webinar has been recorded and we will be putting it up on our website. And when we are able to do that, because we have to go through a number of processes to do it, we will send out an email to all of you and letting you know that it's up. So before we sign off, we just want to remind you that EPA's Soak Up the Rain resource page is on our Soak Up the Rain website at www.epa.gov, Soak Up the Rain. So please visit. If you have questions or comments about our resources and tools or about these Soak Up the Rain webinars, please send us an email at soakuptherain, one word, at epa.gov. Here's a screenshot of our homepage. How to soak up the rain includes BMP information on rain barrels, rain gardens, trees, and permeable surfaces, what they are, and how to implement them. We also provide links to New England-specific resources, connecting you to information from our states, cooperative extensions, and other groups. Each BMP description is accompanied by a photo gallery depicting applications from around the region. It also includes municipal and community resources, including active local organizations and potential GI funding sources, a What's New section that includes news about upcoming webinars, other events, and new publications, and outreach tools, which includes our collection of Soak Up the Rain ready to use and customizable versions of outreach materials that can be tailored for use by your agency or organization. Here's an example of GI posters and business cards that can be customized with your logo and address. And if you wish to follow up with Jamie, his email address is james.oule@unh.edu. I think that is already up on the answers to questions there. So thanks for attending. Thanks to George Burgos for his technical support. We hope you'll continue to join us for upcoming webinars, and don't forget to notify us about topics that you'd like to see discussed in future. And finally, please take a moment to fill out the evaluation you'll receive after this webinar. Your responses are important to us, and we do act on them. This concludes today's webinar. Thank you.
Thank you, Jamie.